So next we're going to look at graphing multivariable functions. It's chapter 14.1. Our learning goals for this set of videos is to understand the notation for multivariable functions, to find the domain of multivariable functions, to graph multivariable functions, and the graphs of these will include a vertical trace, a horizontal trace, and being able to create contour plots. In addition, we will have the skill of being able to calculate an estimate of the average rate of change given a contour plot, and also to understand the graphs of level surfaces. So let's start by looking at the notation of single variable functions and move towards notation of multivariable functions. So as you recall from middle school algebra, when you're dealing with a single variable function, it's typically written f of x equals y, where x is your input and y is your output. And when you graph something that's f of x equals y, we know that on our x-axis we have our input value, on our y-axis we have our output value, and it's typically notated as an ordered pair. Yeah, Carolyn, that's boring. You knew that since middle school, right? So let's talk about a two-variable function. In this case, we're going to have two inputs, both x and y. And our output is typically going to be denoted as a z, because that's the next letter in the alphabet. How does this look graphically? It means that our inputs are inputs from the x, y plane. And I'm typically going to draw my picture like this, meaning that I'm visualizing a flat surface in the xy plane, and that's where my input is coming from. My input is going to have some x value, and then it's going to go over some y value amount. And so my input is here at x1, y1. And the output is whatever I get out of the function, which I denote graphically by going up a distance z. So my point is called the point x, y, z, where the x and y are the inputs, and my z value is the output. And this generalizes. So if I wanted to, I could have three variables as my inputs. I could have x, y, and z all as inputs, and then w would be my output. This is much trickier to visualize because in this case, my inputs are in three-dimensional space, right? My input is taking up all of x, y, and z coordinates. So let's say my input is out here at the point x, y, z. How do I denote the value w as the output? Typically, when we look at this graphically, we have to think of this as another value. So we could think of it as in terms of color, that you can have different colored surfaces to denote the fact that all of those w values are the same. We'll get to that more when we talk about level surfaces at the end of this video set. So that's my notation. Let's talk a little bit about how you calculate the domain of functions like this. So let's say that I have a two-variable function. That's the type of function that we're going to deal with most commonly in this course. F of xy is equal to the function, let's say, x plus square root of y. And notice that if I give, let's do an example, let's say that x equals 1 and y equals 4. This is the point 1, 4. My output in this space is going to be 1 plus square root 4, which is square root 4 is 2. I end up with 3 as my z value, my output value. What's the domain of this function? Recall that the domain are the possible input values that can work in this function and give out real outputs. We see that any value of x will work. There are no restrictions on x. So x is all real numbers. But there is a restriction on y. Y has this square root sign, and you know that to stay within the real numbers, we can't enter a negative input in for y. So y has to be greater than or equal to 0, because if we were to input a negative number in here, it would get us out a complex number, which is not in the real numbers. And generally, Most of the functions that we will deal with have, generally, maybe I'm not going to write the full sentence. The domain is typically all reals unless we have something bad. And what are the things that are typically bad? If we have a radical sign, square root sign means that our values have to be greater than or equal to 0. We could also have the restriction that, let's say that I have 3 over x. That means that x cannot be equal to 0, because if it were equal to 0, then the denominator would be equal to 0. And more generally, we need to make sure that the denominators are not equal to 0. So it's much like finding domains for single variable functions. You just have to make sure that you list what domain values work for both x and y, or if you had a 3 variable function for x, y, and z. Let's take a look at planes. And I don't mean airplanes, because, that would be a different course. We're talking about planes in 3-dimensional space. So I'm going to name a couple of the common planes that we're going to talk about and visualize them with you for a second. So again, this is my representation of 3-dimensional space on this flat surface where I have my x coordinate sort of coming towards us at an angle. If I talk about the xy plane, that's the plane that's comprised by the x-axis and the y-axis together. So the xy plane, when I draw it spatially, I'm going to draw it like this. It's the flat thing sort of at the ground of this function. And the z-axis is extending up out of this plane. Similarly, if I were to talk about the zy plane, in this case, because the x-plane or the x-axis is what's coming out towards us, the zy plane is what contains the z and y axis. So if I were to think about this visually, I might color in a plane that is flat back here. Obviously, because I'm trying to represent 2-dimensional objects within a 3-dimensional surface, you can't exactly see the fact that this is what that plane is. Finally, let's say I were to talk about the plane y equals 3. First, we might want to step back and say, well, what does that mean? What are the values for which y is equal to 3? If I look at this graphically, again, I'm setting all of my y values equal to 3. 1, 2, 3. It means that my z value can be any set of values. So it means any of the values where z is positive or negative are going to work. We also have that x is unrestricted. So if y is equal to 3, really what I'm saying is I'm taking a slice parallel to the xz plane that's traced out by these two dotted, those dotted lines are too dark or too light. Here's a darker dotted line, and here's a darker dotted line. And it means that the plane y equals 3 is a plane that looks something like this. It's exactly parallel to the xz plane, but it's sticking out where y equals 3. So I'll write that down. Y equals 3 is a plane parallel to the xz plane, but where y equals 3. This is necessary to be able to talk about our next tool in visualizing 3-dimensional or multivariable functions. Our next tool is to talk about vertical and horizontal traces. So let's start just by diving into an example. Let's say that we have a multivariable function given by f of xy is equal to x squared plus y squared minus 2. And I could plot some points and start graphing some points along here, but we're going to be wise about the way that we plot points so that we can get a visual image for what's going on a little bit more rapidly than if I were to just randomly start picking values of x and y. The first thing that I'm going to do is I'm going to set y exactly equal to 0. So if I set y equal to 0, maybe I'll keep track of this over here. No, I'm going to do this on a separate sheet of paper. Sorry. If I set y equal to 0, what does that give me for the function? It means that my new function, f of x, 0, I'm plugging in 0 for y, I get the equation x squared plus 0 minus 2. And we know what this is, back from our algebra days, that this is just a parabola that's been shifted down by 2. And so if I wanted to visualize what this would look like in my old school thinking, I would know that if this were the x-axis and this were the z-axis, my outputs I'm now labeling as z, it's going to give me a parabola that looks something like this, right? It has intercepts at square root 2, plus and minus square root 2, and it dips down till it hits negative 2, because when I plug 0 in for x, I get out negative 2. Great! So this is a start of one slice of our three-dimensional function. Which slice is it? It's the slice along the plane where y is equal to 0. Y equals 0 is along this xz plane, and we just found out that if we wanted to think about graphing this, I'm going to extend my axes a little bit. We just found out that along the xz plane, I have an intercept down here at negative 2, which is the point negative 2 for my x value, 0 for my y value. Oops! Sorry. It's 0 for my x value. What did I plug in for x? I plugged in 0 for x. I plug in 0 for y, and what do I get out? Negative 2 for my output. So that's one point on this graph. And in fact, all of the points along this parabola are going to be on this graph. The parabola is a little wonky, but this is the parabola that has intercepts where y is equal to 0, so I'm thinking that I'm along this flat angled plane, and I have the point square root 2 is an intercept, so where x equals square root 2, where y equals 0, z is also equal to 0, and where x was equal to negative square root 2, y was equal to 0, and z was equal to 0. So this has a very special name, this graph of a parabola. We're going to call this a vertical trace, where y equals 0. If we wanted to think about it, it's because we're looking at a vertical slice of our three-dimensional function. It's the slice where y equals 0. And if we did an infinite number of slices, if we did a slice for each of the y values, you could see that it would trace out the entire function. We're just going to do one more slice. Let's do a vertical slice where y is equal to 2. That means that our function, x can be a variable, y is equal to 2. That's going to be equal to x squared plus plugging 2 in for y, I get 2 squared minus 2. So what does this look like? This is a function f of x2 is equal to x squared plus 4 minus 2 plus 2. Again, this is a parabola. This is a parabola that's been shifted up to have an intercept at z equals 2. So in 3 dimensions, this is going to be the point where x is equal to 0, y was equal to 2, because that's what we set y equal to, and our output value z was also equal to 2. So let's plot this new parabola on our graph. We have to be careful, though, because this new parabola is along a different slice. It's along the slice that's been stepped out a little bit. It's the slice where y is equal to 2. So if I'm thinking of taking a slice that's again parallel to the xz plane and tracing it out, I know that this slice will be a parabola that has a vertex at, let's see, x is equal to 0, y is equal to 2, and z is equal to 2. So I stepped up 2, and I get another parabola up here. So far, this might not be very helpful in telling me what the function looks like. But if I did an infinite number of these, you would find that you would get an infinite number of parabolas. And they trace out a parabola. This is one way of thinking about this function. There's another way of thinking about this function. These were all vertical traces. Let's do a horizontal trace. So keeping with the same example, we're still going to have the function f of xy is equal to x squared plus y squared minus 2. But now when I look at my horizontal traces, horizontal trace. What's a horizontal trace? Instead of setting y equal to a fixed value or setting x equal to a fixed value, I'm going to set z equal to a fixed value. So I'm going to set z equal to 0. It's a reasonable place to start. What does that mean for this function? That means that this function becomes 0 because z is exactly equal to my output values. So 0 is equal to x squared plus y squared minus 2. If I wanted to add 2 to both sides to make it look like a more standard form, 2 equals x squared plus y squared. This, you may or may not recall, we could plot a bunch of points to find out what this looks like, but this is a circle of radius square root 2. And I'm going to have this as an aside. It should be a review for you, but it's something I expect you to know for this course, that in general, r squared equals x minus a squared plus y minus b quantity squared is a circle of radius r and center at the point a, b. This is shifting it a units over, this is shifting it a units up, and the only thing that's tricky to remember is that by Pythagorean theorem, x squared plus y squared equals hypotenuse squared, and in this case the hypotenuse is the r. So if I'm given a function like this, to find the radius, I know that 2 is equal to r squared, so the radius must be the square root of 2. This is a review that I want you to know. But what does that mean for our horizontal trace? For our horizontal trace, this means that when z equals 0, we have a circle of radius square root 2. So when z equals 0, that's the xy plane, and it means that I have a circle down here of radius square root 2. Shum, shum, shum. And if I were to do this for another value of z, let's take a trace where z equals 1. What does that mean for our function? That means that 1 is equal to x squared plus y squared minus 2. And I add 2 to both sides, and I see that 3 is equal to x squared plus y squared. So that's a circle of radius square root 3, which is a little bit bigger. So it means as I move up, I have a new radius that's a little bit bigger. And as I keep moving up, if I kept plotting these, I'm not going to continue doing it by hand, I get circles that are bigger and bigger and bigger. And when do they get smaller? They get so small, if you check it out, if z equals negative 2, notice that means that negative 2 is equal to x squared plus y squared minus 2, plugging it into our function. And we see that that's when 0 is equal to x squared plus y squared. The only way that this solution can occur is when x and y are both 0. So that's telling me when z is equal to negative 2, x and y have to be 0. And that corresponds exactly with what we found when we were doing our vertical traces. So what does this picture look like? Putting these two pictures together, we found our vertical traces was this set of parabolas. We found our horizontal traces are these sets of circles, And together you can visualize what's going on in this graph, right? Together it's this expanding set of circles. It's sort of like a bowl, right? That's opening upwards, that gets bigger and bigger as you travel in the vertical z direction. There's one final thing that I want to mention before we go on to looking at contour plots in more detail. It's something I want to define as a contour plot. So let's say instead of messing around with plotting these on a three-dimensional surface, I just want to plot them in 2D time. Contour plots are actually sort of a top view of the graph of a multivariable function. So for example, the contour plot of this function, this is my same example as before. This is the function f of xy is equal to x squared plus y squared minus 2. If I'm looking down from above, instead of being a three-dimensional plot, it's just going to be our favorite old two-dimensional plot, the way that we're used to. And as I look down, my contour plot is going to consist of all of my horizontal traces. So the contour plot is a set of horizontal traces. Or in this case, we found when z was equal to, which one was the one we started with? I guess we started with z equals 0. We found a circle with radius square root 2. When z was equal to 1, we found a circle with radius square root 3. When we had z equals negative 2, you can imagine me continuing on and on with this, and the contour plot is going to be the set of these horizontal traces. And we notice that in this case, they aren't growing in linear time. That when z equals negative 2, it's just the point 0, 0. So maybe I'll include that. That's not really a trace, but it's just a point. That as my function grows steeper and steeper, these contour lines are going to get closer and closer together, right? Because as I'm looking down from the top, if they move apart slowly, you'll have more space in between. It corresponds with a less steep incline. I'll write that down. If contour lines, which are exactly the horizontal traces, are close together, the 3D graph is steeper. What do I mean by steeper? I have a greater change in my x value as I move along in my xy plane. We're going to explore this in a little more detail when we do our lab.